Some functions, like this one, have a well-defined slope. Remember that slope is the rise over run. So if we fit a triangle under the function, we can look at this rise, this run, and the slope is the ratio of those. But not every function is so easy to work with. Look at this. Here we have the median weight of babies versus their age in months. So if I look at my son's mass and I want to know how quickly is his mass changing when he's 9 weeks old, or when he's 20 weeks old, or when he's 27 weeks old, if I look at the change in mass per change in time, I'm not always going to get the same answer. So if we look around 10 months, what does 1 month change in age produce for a change in mass? Well, we can see, comparing the before and after, that around 10 months of age, a baby gains about half a kilogram. But if we look earlier, around 4 months of age, for the same change in the horizontal variable here, age, we're getting a much bigger change in the output or weight. So a baby gains about a whole kilogram around 4 months, but around 10 months they're only gaining half a kilogram. How do we define slope for a function like this if the slope is changing? Is there a well-defined way to do this at all? These are good questions, and questions people have thought about for a long time. One of those people was Isaac Newton. Another person was Gottfried Leibniz. They both thought about the same question. They looked at data, and when they looked at it, they came up with a tool to analyze how the data changed. They had different names for their tool. They also used different symbols. But today, we realize they invented the same tool, which they like to fight about. The tool is called calculus, and one part of it is what we're talking about today, derivatives. What are they? How do they work? Well, we want to start by talking about time. In physics and in language, time refers to two ideas. The first is an instant in time. This answers questions like, what time should we meet? The second idea is a period of time. And that answers questions like, how long will the meeting last? How do these things differ? Well, I can define average velocity over a period of time, but do I also have a velocity at every instant during that duration of time? We can arrive at an answer by making the duration of time shorter and shorter until it looks like an instant in time. And that is the idea that Leibniz and Newton came up with. So let's look at an example. If I plot time on my horizontal axis and displacement on my vertical axis, and I want to imagine that you're traveling from home to school. Let's put some coordinates on here. After 5 minutes, you've traveled a quarter mile. After 10 minutes, a half mile. I think you see the trend. After 15 minutes, 3/4 of a mile. So every 5 minutes that go by, you're traveling another quarter mile. And after 20 minutes, you reach school 1 mile away. So clearly there's a trend here. This looks like a case where we have a well-defined slope or a well-defined average velocity. So what is your average velocity here? Well, let's look at the whole time period. The definition of average velocity is that we take our final x, subtract our initial x naught here, and then we divide the result of that difference by the final time minus the initial time. So over this time period, here's our initial position and initial time. They're both 0. And our final time is 1/3 of an hour, or 20 minutes. Notice that that's 1/3 of an hour. And 1 mile. So let's calculate what the average velocity is. It's going to be 1 mile minus 0 miles over 1/3 of an hour minus 0 hours. So that's 1 over 1/3, which we know is the same as 1 times 3, or 3 miles per hour. So let's look at a different interval of time. We're going to look from 5 minutes to 15 minutes. So what fraction of an hour is 5 minutes? Well, it's 5/60ths. So that's 1/12 of an hour. And our position, we start out at 1/4 of a mile. So if we apply the same definition, we're going to take the difference in displacement, 3/4 minus 1/4. Here's 3/4 minus 1/4, divided by 1/4 of an hour minus 1/12 of an hour. So that's 15 minutes minus 5 minutes. That's 1/2 divided by 1/6. You can find the common denominators there. That's still 3 miles per hour, not surprising. We can shorten and shorten the time period. And if you notice here, I have 5, 10, 15, 20 blocks representing a mile. And I also have 20 blocks representing 20 minutes. That means if I look at just one block here, the dimensions of that block are 1 minute by 1/20th of a mile. And here you can see the slope of that little triangle right there is a 20th divided by 1. If we multiply that out, if I'm going a 20th of a mile every minute times 60 minutes, then I'm going to have 1/20th of a mile divided by 1/60th of an hour. So let's look at another example, a little bit more complicated. Let's suppose we again start at 0, 0, but after 1 second we've traveled 1 meter, after 2 seconds we've traveled 4 meters, after 3 seconds we've traveled 9 meters, do you see the pattern? After 4 seconds we've traveled 16 meters. Now I bet you see it. Let's fill in the pattern there. So this looks like our position as a function of time is time squared. So suppose I want to know how fast I'm going at some period of time. Let's say between 3 and 4 seconds. What's my average speed? How can we figure that out? Well, I know it's the change in position divided by the change in time. Change in time here is 1 second, so that looks nice. So our average velocity in this case will be 16 minus 9 over 4 minus 3. So 16 minus 9 is 7 divided by 1. So we have 7 meters per second. Let's label these axes, meters and seconds. So let's look at a different period of time. Suppose we look a little bit earlier. From 2 seconds to 3 seconds, what is our average velocity during that time period? Well, here I see that it's going to be, the average will be 9 minus 4 over 3 minus 2, so that's 5 meters per second. But what if I want to know what is my speed at 3 seconds? Well, clearly, before 3 seconds, my average speed had been, for some amount of time, 5, and after 3 seconds, my average speed is going to be 7 over some period of time. So in between, the average speed better be some number between 5 and 7, I think, because it looks like this is getting steeper, which means getting faster. Is there another way we could measure this? Well, we could look at this interval going from 2 seconds to 4 seconds. What would our average speed be then? Well, the average then is going to be 16 minus 4 over 4 minus 2, so that's 12 over 2, which is indeed 6 meters per second. So whereas we got a speed out here of 7 meters per second, can't see that color, 7 meters per second, and back here it was 5 meters per second. Averaging over the whole interval, we're getting 6 meters per second, but I don't know, if I shrink down that interval, am I still going to get a slope of 6 all the time? If I want to know what exactly is the speed at 3 seconds. Let's look at another time. Suppose I look at 2 seconds. Well, I could take an approach of getting an answer that's not right. I'll find this slope between 2 seconds and 4 seconds. But then what if I move this point closer? And I keep connecting the 2 points. I can move the 2 points closer and closer until they are the same point. And then what is the slope of this line? Here's a line that shares only 1 point with this curve. We have a name for that. We call it a tangent. What is the slope of that? Well, here I can see that the slope is 4. So it looks like this curve has a slope of 4 at the value 2 seconds. But let's get away from numbers and just look at the idea. So what if I call the point that I'm interested in x0 or x0, and a short distance later, a distance h further along x, I'm going to have x0 plus h. Along my vertical axis, I have a function of this variable x. So my initial value for that function is going to be the function evaluated at x0, and then I have the function evaluated at x0 plus h. So the slope we're looking for is the slope of this triangle here, the rise over run. And we want to know what that slope will be when we make the triangle very tiny, when we shrink it down. So we can make a definition. The definition we're going to use is going to be that the slope of this function, which we'll call f prime, will be the ratio in the limit that that quantity h becomes very small as it approaches 0. So the limit as h approaches 0 of the function evaluated at x plus h minus the function evaluated at x itself. Which x is this? x0. And here our change is x0 plus h minus x0. Notice I'm subtracting this here, so that cancels out. So my definition is going to be the limit as that little change h approaches 0 of f of x0 plus h minus f of x0 divided by h. That's f prime evaluated at x0. But of course, x0 is arbitrary, so this is true for any x. So that's the definition of the derivative. Let's make a little more space here and see what happens with this function. Shrink it out of the way. So I can tell that the slope here at t equals 0, I'm back, let me point out, to calling the function x, it's our position, and x prime is the rate of change of x, which we also call velocity. So here, where the slope is 0, x prime is going to equal 0. So we're going to map that down. Value is 0. And at 1, the slope is 2. At 2, the slope is 4. At 3, the slope is 6. I think you see the pattern. So when the function is t squared, the derivative is 2t. At 1, I get a value of 2. At 2, I get a value of 4. 3, I get a value of 6. 4, I get a value of 8. So there are two mappings happening here. We're mapping, when we talk about mappings, we're saying that we assign, for a value x, we assign that value to a number f prime of x, that represents this limiting slope. So that's the first mapping. The second one is that we're creating a relationship between this function and the related function f prime. So we're actually saying there's a way to get from this function to a function that has the slope of this function stored at every location along the function. So the same way that a function maps a variable to a number for every value of that variable, here we have some notation that we call this an operator. This is the derivative operator, and that operator maps a function to another function. So in our next video, we're going to look at how to use this definition of the derivative to actually find the functional form of the derivative of some simple functions.